Welcome to a model for chemical kinetics. So, to discuss the rates of chemical reactions, we need to develop a model for how reactions occur at the molecular level. So to do this, the model that we use is the collision model. So the collision model states that molecules have to collide in order to react. So if we have, say, this blue molecule here and this gray one, if those molecules don't collide with one another, then they can't react. It's only molecules that are colliding that can react, and they only are able to react in the instant that they collide. At any other time when they're separated, they're not able to react with one another. So, this can explain the concentration dependence of our reaction rate. Because if our molecules have to collide in order to react, then the rate should be high when our concentration is high, because the molecules are likely to collide. So if we have a low concentration of our molecules, then we have relatively few collisions between them in some period of time. And if we have a higher concentration, then we have a lot more collisions in that same period of time. But our reaction rate is much lower than the collision rate. So the collision rate is fairly high because our molecules are moving around fairly rapidly, at least at room temperature they are. But that doesn't mean that every time the molecules collide, or reactants collide, they react. Our reaction rate is in fact far lower than the collision rate is. And this is because only a small fraction of our collisions actually lead to a reaction, for a few reasons. So, Svante Arrhenius proposed the existence of an activation energy, and I'm going to symbolize this E sub A. So this activation energy is a quantity of energy that the collision must contain in order for the reaction to proceed. Which means that if our molecules are coming in and they're moving relatively slowly, at least with respect to one another, then when they collide with one another, there isn't much energy there, and they're not able to react. Now the reason for this is because molecules, in order to react, usually have to break some chemical bonds. They have to break some bonds that are already present in the reactants, and breaking bonds requires energy, so you have to break the bonds, and then later you can form bonds. So you may still release energy overall, but you have to put in some energy to break those chemical bonds in the first place, and then you can go on and form some chemical bonds, and only after those chemical bonds have been broken, the chemical bonds in the reactants. So if our molecules collide with less than the activation energy, then no reaction occurs when they collide. And this means that if only a small fraction of our molecules have that activation energy, or only a small fraction of our collisions have that activation energy, then only a small fraction of our collisions will actually lead to a successful reaction. So the activation energy comes from the kinetic energy of the molecules before collision. If the molecules are moving fast, then there's more energy available during the collision to break the chemical bonds. If the molecules are moving slowly, then there's less energy available to break the chemical bonds. So the activation energy, again, is used to break bonds in our reactants that have to be broken during the reaction. So if the molecules don't have enough energy, then those bonds can't be broken, and then the reaction can't proceed, because those atoms won't sort of want to form bonds with any other atoms. So let's examine the decomposition of ofBrNO. So we have two molecules react to give us two NO molecules plus bromine gas. And in this reaction, two of our bromine nitrogen bonds have to be broken. And it takes 243 kilojoules per mole of energy to break each bromine nitrogen bond, which means we're going to, because we need to break two of them, we're going to need double that amount of energy for our reaction to take place. So we start out with our two BrNO molecules. We end up with two NO molecules plus a bromine molecule. There's some energy change between them. In this case, it's somewhat exothermic. But we end up having to put in a significant amount of energy to break that bromine nitrogen bond. Note that up here we get to a transition state. So this is the point at which we're sort of transitioning from having our bromine-nitrogen bonds. We're starting to break those bonds. We've almost totally broken them, and we're starting to form our bromine-bromine bond. So I'm not sure if you can see, but in here we've got these dotted lines between the bromine atoms and the nitrogen atom, and we've got a dotted line between the two bromine atoms showing that those bonds are halfway formed, halfway broken. And then after that transition state, so now on the left side of the transition state, the bromine-nitrogen bond is stronger, and as we move to the right, that bromine-nitrogen bond gets longer and weaker, and the bromine-bromine bond gets shorter and stronger as we move to the right. So as we are on the right side, those bromine atoms are attracting each other and releasing energy then to get us back down here to our products. And so you can, again, look at it sort of from a molecular point of view instead of with the letters over there. So in this case, the oxygen atoms are red, the nitrogen atoms are blue, and the bromine atoms are this sort of pinkish color. And we start out with our two separated molecules. As they get closer together, if they're in the right orientation, they may collide and react, and we get up here sort of our dotted bonds here, dotted line bonds, and we're breaking these two bonds, and we're forming that bond there until we get down here, and we have now our two NO molecules and our bromine gas molecule. So the arrangement of atoms at the top of our hill here, again, is our activated complex or our transition state. So in this arrangement, again, our bromine-nitrogen bonds are stretched and they're almost broken, while the bromine-bromine bond is just beginning to form. So again, breaking bonds requires an input of energy, so we have to go up on this potential energy axis, while forming bonds releases energy, and so we're going down on our potential energy axis. So this means that breaking the two bromine-nitrogen bonds requires inputting energy. We have to go up. That energy, again, is our activation energy. And then forming the bromine-bromine bond releases energy. In this case, it happens to be more than the activation energy, more energy than we had to put in. So that difference in energy between the input and output energy is delta E. Note here that delta E doesn't influence the reaction rate. It doesn't determine how fast the reaction occurs. Now that delta E is this distance here, from the distance from the reactants, so that line over there, to the products. That change in energy does not determine the reaction rate. The reaction rate is, however, influenced by the activation energy, which is the energy difference between the reactants and our transition state. Right? So this energy does influence the reaction rate. This one does not. Now, the activation energy does influence the reaction rate because, again, we have to put in that much energy. So if we need to put in more energy, if the activation energy is higher, then a smaller fraction of our molecules will have that much energy, and a smaller fraction of our molecules will be able to react, which means the larger the activation energy, the lower the reaction rate is going to be. Conversely, the lower the activation energy is, the more molecules will have that, or the more collisions will have that much energy or more, and then we will have a higher reaction rate because more collisions, a larger fraction of our collisions will be able to form our products. We'll be able to go ahead and react. So, what influences our reaction rate? The activation energy, and again, the lower the activation energy, the higher the reaction rate is. The temperature influences the reaction rate, and the molecular orientation. So, the temperature influences the reaction rate because we have our molecules moving. The faster our molecules are moving, because as we heat up, our molecules start moving faster. We're giving them more kinetic energy. As we heat up our reaction, our reactants and products, our molecules are moving faster. The collision rate goes up. Even if the success rate of a collision leading to a reaction remains the same, we're still having more collisions per unit of time, and that means our rate should go up. Again, our activation energy is influencing our reaction rate because if we plot the number of molecules that have some kinetic energy, this curve isn't totally drawn right, but it's close, we have a curve that looks something like this, and so it's exaggerated over here on this end. Note that if the activation energy gets lower, then more of our molecules are to the right of this line. They have to be to the right of the line in order to react. Right? They need to have at least that much energy, because they need at least that much energy to break the bonds that they have in existence in the reactants already. We have to break those bonds before we can start forming the bonds in the products. So again, the higher the temperature is, the faster the molecules move, which increases the collision rate, which then increases the reaction rate. The higher the temperature is, the higher the average kinetic energy of our molecules is, which also then increases the likelihood that a collision will have enough energy to overcome the activation energy. Because remember, again, if we plot our curve of our number of molecules versus energy, kinetic energy, right? We have our activation energy there. Well, as we go from a relatively cold temperature, T1, the blue curve here, to a warmer temperature, T2, we shift the curve to the right. More of our molecules are at higher kinetic energies. So not only are molecules moving faster and they collide with one another faster, which alone will drive up the reaction rate, we also have a greater fraction of our molecules with that have the activation energy. So not only do we have a higher collision rate, we also have a higher success rate, as it were, once our molecules do in fact collide. So the last thing that we need is the correct molecular orientation. So in this reaction, we have to have our molecules come together side by side, and then we can have our bromine atoms form a bond. And so we can in fact have a reaction occur if the molecules come together with this orientation. If our molecules come together with our bromine atoms, with sort of the bromine ends of the molecules striking each other and the oxygen ends pointed away from each other, we can still have a reaction because, again, we need to have those two bromine atoms form a bond, and our NO molecules can go flying out sort of sideways. But note that if we turn them around, and now we have our oxygen atoms coming together, well, now we're not interested in forming a bond between our oxygen atoms. We need to form a bond between the bromine atoms, but the bromine atoms are too far apart now. And so in this case, they're going to collide and they'll bounce off of each other. So the molecular orientation has a big part to do with whether or not the molecule will react. Because even if they have enough kinetic energy, if they strike in the wrong orientation, we still can't form the bonds and the products that we need to form. So even if in this collision we're breaking a bromine-nitrogen bond, the bond will just form again almost immediately because that bromine hasn't then formed a bond with the other bromine atom. So we can combine these three factors together into an equation. Note that it's derived in the Zumdahl textbook. I'm not going to derive it here. We can use this equation to determine the activation energy using the rate constants at two different temperatures. So we have the natural log of the rate constant at some temperature, K2, divided by the rate constant at some other temperature, K1. That's equal to the activation energy, EA, divided by R, the gas constant, times the quantity 1 over T1 minus 1 over T2. T1 and T2 are the temperatures at for the rate that we measured here, the rate constant K1 and K2, respectively. So that was a model for chemical kinetics.